Let's learn some physics. Acceleration style. You might remember acceleration is defined as the change in velocity in a period of time, or in this case, I'm right every second to make you understand something. A with a line over it represents velocity over time. The line means it's a vector, and it's the vector. It's got magnitude in amount and direction, positive, negative, left, right, whatever. But first, let's talk about an example with signs. I'm slowing it down a little bit here because it's pretty important. So let's take a look at a car. There are a couple different scenarios for it. So let's write down the car, the displacement, the velocity, and acceleration. And let's organize yourself. Yeah, I know I made a little error in that line. My bad. The first case is a car going constant velocity forward, which means its displacement is positive because he's on getting further from its start. And the amount every second it gains in distance is the same. So the displacement is going up at a constant rate. The velocity is positive, and it's a constant. It's not changing, so the acceleration is 0. Next up, let's look at a car going forward but speeding up. The displacement's positive, of course, keeps it getting further and further away. The displacement's going up every second, and it's increasing at the rate. So the velocity is positive and also increasing, which means the acceleration is positive as well. The third situation, a car going forward but slowing down. The displacement's still positive. It's still gaining displacement every second, but it's gaining less and less displacement. So the velocity is still positive, but it's getting closer to 0, which means the acceleration is negative. Let's keep going. Now let's assume that same car, which went forward, slowed down, and stopped, is now going backwards. So what happens? Well, at first it's positive because it stops, and even though it keeps on going backward, it's still forward in front of its start point. So it's got an increasing displacement at a decreasing rate until it hits 0, and then it's positive, but losing displacement until eventually it gets back to its start point. The velocity is first positive, but decreasing to 0, and then it's going to be negative and increasing because it's going backwards. So the acceleration the entire time is negative because it's losing positive velocity at first, and then it's gaining negative velocity next. So now let's look at a car going backwards and speeding up. The displacement's negative. It's ending up behind where it started. The displacement is increasing at an increasing rate. You're gaining more and more backward distance every second. The velocity is negative and getting faster, which means the acceleration is also negative because it's gaining more and more negative velocity every second. And finally, the car going backward, it's slowing. Displacement's negative, and it's increasing at a decreasing rate. The velocity is negative, but it's going to 0, which means the acceleration is positive because it's gaining positive velocity, or it's losing negative velocity every second. To think about the math, think of an example where a car is going 16 meters per second with an acceleration of 3 meters per second. But since it's the vector, we've got to have direction for both of them. There we are, positive both ways. So what would the velocity after 4 seconds be? Well, here's how you think about it. At time equals 0, it's going 16. Every second, it's gaining positive 3. 19, 22, 25, 28. So we figured out the velocity is 28 meters per second, positively. Now let's look at graphs. To begin with, let's draw a constant velocity graph, which means that the displacement is going up at a straight line, a linear relationship. The slope of displacement is velocity. Since the slope is constant, the velocity is constant as well. This shows us that the displacement is getting larger, and it's positive, which is our first example from the car example. So we could draw the velocity as that straight line. The slope of the displacement is the velocity, so that line, slope on the left, is equal to the value of the line on the right. No acceleration. If you draw the acceleration graph, it would just be a line directly at 0. Now let's take a little more interesting case. Let's do a curved line like that. To show what's going on, I'm going to look at 3 just random parts of it. I'm going to take the slopes there. It starts off with a very low positive, then a mid positive, then a very high positive. Since slope is velocity of displacement, that means the velocity is getting more and more and more. So I could draw that line. That's the velocity line. It starts off small, but it gets bigger and bigger and bigger. Since it has a constant slope, the velocity is positive. The acceleration must be positive as well because of the positive slope. So the slope of velocity is the acceleration value, which means I'm going to draw a straight line across, and that value of that line is the slope of the one before it. Also, if I look at some time t in both displacement and velocity, the area underneath the velocity graph is the value of displacement in the displacement graph. So, if the displacement is 10, I calculate, that should be the area underneath the curve of velocity for that time period. Let's look at one more graph. Here we have a curve. I draw the 3 lines as well. It starts off very negative, less negative, then almost to 0. So the velocity is negative but going down to 0. So it starts off very negative and then ends up at 0 as you see the red line. Again, the displacement value equals the area underneath the curve. Since displacement's negative, the area underneath the curve must be negative. It's underneath the x-axis. The slope of that line shows the velocity going from negative to 0, which is a positive acceleration, and that's what I draw right there. See ya.